This is your presenter, Asloob Mudassar, and I am presenting slide number 144 of the course on the laser physics. The question is, discuss laser operation in a semiconductor laser, including both Homo junction and double heterojunction lasers. How do the quantum well lasers differ from the DHL? That is how the quantum well lasers differ from the double heterojunction lasers. The answer is active medium in a semiconductor laser is based on direct gap material. These materials are based on a combination of elements from the third group, for example, aluminium, gallium, indium, and the fifth group, for example, nitrogen, phosphorus, arsenide, and antimony of the periodic table, and are referred to as 3 and 5 compounds. Important materials are gallium arsenide, aluminium gallium arsenide, indium gallium arsenide, and indium gallium arsenide phosphate. The wavelength range covered by the third and 5 compounds is from 630 to 1600 nanometer, and some part of a blue-green spectrum also. Semiconductor laser materials are also based on wide gap semiconductors formed from the elements in the second group, including, for example, cadmium and zinc, and the elements in the sixth group, for example, silicon and cesium, referred to as the second and sixth group compounds. The mid-infrared range from 4 to 29 and for mid-infrared range from 4 to 29 micron, fourth and sixth compound requiring cryogenic temperatures are used. Quantum cascade lasers cover the same range but at room temperature. Assume a non-degenerate semiconductor held at temperature T is equal to 0 Kelvin, where the valence band V is completely filled with electrons and the conduction band is completely empty, as shown in part A of figure number 1. So here you can see that figure number 1, the caption of the figure is valence and conduction bands in a semiconductor before pumping in part A. So before pumping, the structure is shown in part A. You can see that these are the quasi Fermi levels marked as E prime FV, that is the Fermi level for the valence band, and E prime FC for as the Fermi level energy, showing the Fermi level position for the conduction band. And the filled band and the valence band is completely filled, which is shown with the gray shades, and the conduction band is completely empty because the Fermi level is lying at the edge of the conduction band, at the bottom edge of the conduction band. So all the states below the Fermi level, that is E prime FV, that the Fermi level corresponding to the valence band, all the states below that below that Fermi level is completely filled, and all the states in the conduction band above the Fermi level corresponding to the conduction band are completely empty. So we have shown the empty states in the conduction band, which are completely empty, and we have shown the filled states in the valence band. And this is under the condition when no pumping is done. The two bands are separated by energy gap Eg. So you see that I have shown the energy gap over here. This is Eg, which is the band gap energy between the two bands, that is at from the top of the valence band to the bottom of the conduction band. Assume that a pumping mechanism raises some valence band electrons to the conduction band. So here you see that we are going to raise some valence band electrons to the conduction band through the pumping mechanism. Electrons in the higher levels of the conduction band will drop to the lowest unoccupied levels of this band. The electrons vacancies in the valence band will be filled by the electrons near the top of the valence band, leaving holes near the top of the valence band. Quasi-Fermi levels are indicated in the valence band and the conduction band. So now let's explain part B of this figure, which is the part B after pumping by the photon emission. So let me read the caption first. Valence and the conduction bands in a semiconductor before pumping in part A and after pumping in part B. And I have also shown along with photon emission is also shown there. Now you see that in part number B, some of the electrons from the valence band have been moved to the conduction band through the pumping process. And of course, some holes are created in the valence band, and that's why the Fermi level has dropped down. And since some electrons have moved to the conduction band, the Fermi level has risen up. So the electronic states below the conduction band, below the Fermi level in the conduction band are completely filled, and the Fermi and the valence band, the Fermi level in the valence band, all the levels below the below the Fermi level in the valence band are completely filled, and the levels above that contains a hole in the valence band, and the states are referred to as the empty states. You see that the value of the Eg is not going to change because this is the band gap energy between the valence band, between the top of the valence band and the bottom of the conduction band. So through this pumping process, some electrons from the valence band have been moved to the conduction band. So some holes are created at the top of the valence band, whereas electrons at the bottom of the conduction band reside in the conduction band. So the electrons which are moved well above the conduction band, they ultimately fall below and ultimately fill the bottom states of the conduction band, or the states which are just at the bottom of the conduction band. They are first filled, and then of course the other states in the conduction band are also filled. And the emission of a single frequency photon has been shown when the transition takes place from the conduction band to the valence band. So when there is a transition, when there is a movement of electron from the conduction band to the valence band, then of course a recombination process will take place between the electron and the holes, and of course a photon with a frequency h nu will be produced. At 0 Kelvin, all states below the Fermi levels are occupied by the electrons. An electron in the conduction band will move to the valence band and will recombine with a hole, giving off light quanta. This process is responsible for the emission of light from LEDs. So you see that in this condition, when an electron moves from the conduction band to the valence band, that electron combines with the hole there, and then of course a quanta of light is generated. And this process, this is the mechanism that is an ongoing mechanism as far as the LEDs, light emitting diodes, are concerned. The emitted photon can either be absorbed or amplified by the semiconductor material. So you see that if there is no stimulated emission process, then of course this photon will either emitted by the semiconductor material, it could be absorbed by the semiconductor material itself, or it could be amplified if there is a stimulated emission process going on. Photon amplification through the stimulated emission is possible if the following condition is met. That is the energy difference between the two Fermi levels, that is the subtraction of the Fermi level in the valence band from the Fermi level in the conduction band. This energy difference should be greater than or at least equal to h nu, and h nu should be greater than equal to Eg. That is the band gap energy. that is the emitted photon should have an energy greater than the band gap energy, greater than the difference of the band gap energy, and this photon will have an energy less than equal to the energy difference between the two Fermi levels. So let me show you the Fermi levels. You see that the Fermi levels now have moved, and there is a greater separation between the difference of these Fermi levels in comparison with the energy gap Eg. So in the previous part A, you will see that Eg is the same as equal to the difference of energies between the two Fermi levels. But when the electrons has been moved from the valence band to the conduction band, then of course there will be a change of a position of the quasi-Fermi levels. The quasi-Fermi levels corresponding to the valence band will move down, and the quasi-Fermi level corresponding to the conduction band will move up because of the presence of the electrons in the conduction band. And you see that now the gap between the Fermi level in the valence band and the Fermi level in the conduction band is now greater than in comparison with the energy gap between the two bands, that is Eg. So EFC minus EFV is now greater than Eg. And this photon must have an energy, obviously, as obvious from the figure, is must have an energy greater than the band gap energy Eg, and this EH nu will have an energy, of course, less than the difference of energy between these two Fermi levels. So you see that I have shown you this condition, and this is the condition of a photon amplification through stimulated emission. It's only possible if this condition is met. You see that this is a very strict condition because this is a condition where we have the equality sign also. So that is the Fermi level energy difference between the two Fermi levels is at least greater or equal than h nu, and this h nu is at least greater or equal to Eg. So this is a very strict and very tightly fitting conditions. It is found that this also holds for any temperature. So you see that we started our discussion that we are talking about we have shown these we have shown these levels when the temperature is at 0 degree Kelvin, but of course these are also applicable to the conditions when the temperature is not the zero level temperature or is not the 0 Kelvin. So it is found that this also holds for any temperature. A range of transition frequencies nu. So here you see that nu, I have shown only a single frequency, but a range of a frequency can also satisfy equation number 1, provided the gain from the stimulated emission exceeds the absorption losses. So if the difference of energy difference between the two Fermi levels is much greater than the band gap energy, then of course we have a very relaxed condition. So the condition given in 2 is much relaxed in comparison with the condition given in 1. So it means that many photons of a frequency h nu are possible to be emitted under this condition. And of course, this condition will also ensure that the stimulated emission will exceed the absorption losses. So when the gain due to the stimulated emission is well above the absorption losses, then of course the lasing process can only be ensured under that condition. When the density n of the electrons raised to the conduction band increases, that is the density n of the electrons raised to the conduction band increases, that is the level of the Fermi level in the conduction band becomes a function of the density of the electrons. So greater the density of the electrons, the higher the conduction band will move up inside the conduction band. And while the Fermi level in the valence band, which we have referred to as a Fermi level in the valence band as a function of n, will decrease. That is, you move the electrons, that is, if more electrons are moved to the conduction band, then of course the Fermi level in the conduction band will move upwards, whereas the conduction band in the valence band will move downward. So the Fermi level in the conduction band will decrease in energy to the energy level, whereas the conduction band whereas the Fermi level in the conduction band will rise up, that is will gain its energy. Thus for equation number 2, that is this equation to hold, that is the gain exceeds the absorption losses, the electron density n should exceed a critical value given by the condition. So you see that here we are in equation number 3, we are going to discuss the condition where the Fermi level due to density which we call as the density at transparency, that is TR stands for the transparency and TR stands for the electron density at the transparency. So the Fermi level in the conduction band as a function of the electron density at a transparency minus the energy of the Fermi level at the density of the transparency will be equal to Eg. So this condition ensures that there is a change of density of states, density of the electrons, and the density of the electrons. Under this condition, which we have called it as a density at a transparency, which means that the semiconductor material will appear to be transparent. That is, it will neither amplify the number of photons within them, nor the number of photons will be lost. So no photon is created, no photon is generated through the semiconductor material. That's why this condition is referred to as the condition under the transparency. So when the density of the electrons in the conduction band is equal to the density or the density at the transparency, then of course the condition number 3 will hold and the semiconductor will appear to be transparent. That is, it will not be able to amplify any. That is, there will be no amplification process due to stimulated emission, or you can say that the stimulated emission is being balanced by the stimulated absorption. That is, the generation of photons is balanced by the loss of the photons in the form of absorption, where NTR is the electron density at a transparency. So when N is greater than N transparency, that is N is greater than NTR, the semiconductor will exhibit a net gain. When such a semiconductor material acting as an active medium is placed in a suitable cavity laser, light will emerge out as the output beam. So since we have under that condition where N density of the electrons in the conduction band is greater than the N transparency, then of course a net gain will be generated. And if we place such a semiconductor material as an active medium in a suitable laser cavity, then of course light will emerge out as the output beam. That is in the form of a laser beam. Pumping source could be another laser, or an electron beam, or the current flowing in the forward direction of the junction. If same material, say for example gallium arsenide, is used both for p-type and both for n-type materials, the laser is named as Homo junction material. So in case of Homo junction, the p-type material and the n-type material are, you see that use the same semiconductor. That is, for example, in this case I have mentioned as gallium arsenide. If an active medium is sandwiched between different P and N materials, so you see that if you are sandwiching an active medium between P-type material and N-type material which belong to different semiconductors, the laser obtained from such a junction is regarded as a double heterostructure laser, abbreviated as DHL. DHL, which is a double heterostructure laser, can be operated in CW at room temperature. So this is the beauty of this double heterostructure, that the laser operation can be achieved in a continuous way at the room temperature, whereas the cryogenic temperature, that is the lower temperature, is required for the operation of CW from a Homo junction laser. DHL is now being used in a variety of applications areas, and Homo junction laser has only historical importance. So the real junction that can produce laser at room temperature is actually DHL, double heterostructure laser. But for the completeness, we are going to go through some Homo junction theory, so that for the sake of a completeness, we are going to give some knowledge about the Homo junction lasers. In Homo junction lasers, both p-type and n-type regions are from the same material. Due to very high acceptor concentration in p-type, the Fermi levels belonging to the p-type material, which we have designated as EFP, falls in the valence band of the p-type material, whereas due to very high donor concentration in the n-type material, Fermi level that is that is EFN, that is the Fermi level corresponding to the n-type material, falls in the conduction band of the n-type material. So you see that EFP, that is the Fermi level due to the p-type material. In the p-type material will fall in the valence band, and whereas the EFN, that is the Fermi level due to the n-type material, will fall in the conduction band of the n-type material. In the absence of the applied voltage, both the Fermi levels are aligned. That is, both Fermi levels have the same level. That is EF due to p-type material, and the Fermi level EF due to n-type material. Both will be aligned and are aligned with each other, which will be shown in the next diagram. And the resulting band structure is shown in part A of figure 2. So this is part A of figure 2. Let me go through the figure caption of the figure 2 first. Band structure of Homo junction Homo P and junction under no biasing in A and under forward biasing in B. So in part A, no biasing is shown, but you see that we have sandwiched the junction, which is shown in the inclined form over here. This inclined region is actually the junction region, and which we have sandwiched between the p-type material and between the m-type material grown from the same semiconductor. So you see that here I have shown the valence band and the corresponding Fermi level for the p-type material, which falls slightly below the top level of the valence band. And you see that the conduction band is completely empty for the valence band. Even you can see that there are holes in the Fermi level above, in the Fermi level in the valence band. Above the valence band there are holes, but below the valence band, but below the Fermi level in the valence band, all the levels are completely filled. And now we shall move towards the n-type material. You can see that in the n-type materials, one thing which is very important is that the Fermi level due to p-type material and the Fermi level due to the n-type material, that is EFP and EFN, both have the same level. So they exist at the same energy level. But you see that's why I have shown the conduction level below the Fermi level in the n-type material, because some of the electrons have occupied the conduction band. So some states in the conduction band below the Fermi level, that is all the states below the Fermi level, that is below the EFN level in the conduction band, are completely occupied, and of course in the valence band also completely occupied. And the levels above the conduction band above the EFN level in the n-type material, above this Fermi level, are empty. And you see that EG level, that is the band gap level between the Fermi level, between the valence band, between the top of the valence band and the bottom of the conduction band, is also shown and is marked as EG. You can see this is an inclined region which is representing the band gap between the p-type material and the n-type material. And of course, you can see that this slight region, in the tilted region, the top tilted region, has some concentration of the material from the p-type, and this region on the n-type material, at the top of this region in the n-type material, you can see that some region is also overlapping with the junction region. So some electrons has also diffused in the junction region, and some holes from the p-type material have also diffused into the junction region. So you see that when we sandwich the junction between the p-type material and n-type material, then due to the process of diffusion, some electrons from the n-type material will diffuse into the junction, and some holes from the p-type material will diffuse into the junction. So they will diffuse, that is, the holes will diffuse towards the n-type material, and the electrons from the n-type material will diffuse towards the p-type materials in the junction. So the most of the part within the junction is empty when there is no biasing. But you see that when we apply the forward biasing voltage as shown in part number B of this figure, you can see that the junction width, which is denoted by the small separation D, you see that the width of the junction has now reduced because due to forward biasing, more of the holes has moved to the junction, and more from the p type holes has moved towards the junction, and the electrons from the n type material also has moved towards the junction due to the application of the forward biased electric field. And then of course the junction has reduced in width, and the voltage that we have applied is shown as delta E is equal to EV, where V is the applied voltage and E is the charge on the electron. So here we can show that the difference of energy delta E between these two Fermi levels, that is the Fermi levels in the valence band and the Fermi levels in the conduction band, they are separated by an energy delta E, which is equal to EV, and V is the applied voltage. And you see that EG is still unchanged because this is the band gap energy between the top of the valence band and the bottom of the conduction band. So let me go through this paragraph once again. Homo junction lasers. In homo junction lasers, both p-type and n-type materials are from the same material. That is, p-type and n-type regions are from the same material. Due to very high acceptor concentration in p-type, the Fermi levels EFP falls in the valence band of the p-type material, whereas due to very high donor concentration in the n-type, the Fermi levels EFN for the n-type material falls in the conduction band of the n-type material. In the absence of the applied voltage, both the Fermi levels are aligned, and the resulting band structure is shown in part number A of figure number 2, which I have explained. I have also explained the part number B, but now we go through some paragraphs about part number B. When the junction is forward biased with the applied voltage V, the two Fermi levels are separated in energy by delta E is equal to EV, where V is the applied voltage. Under forward biasing and in the junction region, holes from the p-type region are injected into the valence band, whereas electrons from the n-type region are injected into the conduction band. Under biasing voltage, if high current density is set up, laser threshold condition given by equation number 2 can be achieved. So this is under biasing voltage. If high current density is set up, you see that here we are concentrating on the word that high current density is set up, then of course the laser threshold condition given by equation number 2 can be achieved. That is, this condition as shown in equation number 2 can be very easily achieved under the application of the applied voltage and also under the application of the enormous concentration. Or under biasing, that is under the biasing voltage, if high current density is set up, then of course the laser threshold conditions given by equation number 2 can easily established. An electron in the conduction band encounters a small barrier potential in reaching the p side of the junction. The electron penetrates into the p material, acts as a minority carrier. You see that here the electron penetrating into the p-type material will act as a minority carrier and recombines with a hole, the penetration depth of which is given by, so this d is the depth of penetration, which is given by d is equal to the square root of capital T times tau, where tau is the electron lifetime and capital D is the division constant, division coefficient. Small d is found to be much larger, for example, of the order of one order of magnitude greater than the thickness of the depletion layer. That is, the active region is quite thick. So here you should notice that the active region is quite thick, that is thicker than the depletion area. A typical broad Homo junction, Homo p-n junction device is shown in figure number 3. So this figure. So the caption of the figure is a laser beam from a broad Homo p-n junction. So let's go through this junction. So you can see that at the top we have the p-type material, at the bottom we have the n-type material, and in between these two materials we have active region, and the connection is made, the biasing of connections are given to the p-type material, which are shown as the biasing lead to the p-type, and of course the n-type material is also connected with the biasing lead, which is shown at the bottom, and the end surface is a cleaved facet through which the laser will be emerged out as an output beam. And you see that due to small width of the active region, of course, the direction of the beam along perpendicular to the active region will be elongated. So this is because of the diffraction. So the laser beam will expand because of the diffraction, and the laser beam is shown to come out from a broad Homo p-n junction. The thickness of the active region in the direction perpendicular to the junction has a typical value of the order of D is of the order of 1 micrometer. For laser amplification, the two end faces are cleaved and usually not coated, as the Fresnel reflection at the semiconductor air interface is significantly high due to high refractive index of the semiconductor material with respect to the refractive index of the air. Due to the diffraction at the exit window, the transverse direction of the laser beam is of course greater than the actual dimension of the junction, and that value is of the order of 5 micron, whereas the junction size is of the order of 1 micron, and due to diffraction the transverse dimension of the laser beam will be 5 micron. At room temperature, the magnitude of current density, which is of the order of 10 to the power 5 ampere per centimeter square, and this current density is also proportional to L times D, where L is the length of the wafer, as you can see over here, length of this wafer, which is L, and tau and D is actually the separation between the width of the junction, which I have shown, which I have discussed earlier. For example, the junction has a typical value of D is equal to 1 micron. So at room temperature, the magnitude of the current density is of the order of 10 to the power 5 ampere per centimeter square and is proportional to LD, is very high, which can easily destroy the junction and thus prevents the CW operation. So you see that this is the main reason why the CW operation is not possible with the Homo junction, with the Homo p-n junction semiconductor, because due to very high current density, the junction will burn out. Laser beam can extend into the P and N type region where it is strongly absorbed, depositing heat in these regions. So you see that the laser will deposit its heat in the P and N type regions, and of course the semiconductor will be destroyed. The operation of the Homo junction laser in CW mode thus requires cryogenic temperature, that is low temperatures are required for appropriate cooling. The laser gain increases rapidly with the decrease in temperature. So you see that for such a Homo junction Homo, P and junction laser. If you use cryogenic temperatures, that is a much lower temperature, then of course the performance of the laser is improved, and the laser gain increases very rapidly with the decrease in temperature. Now we describe the double heterostructure lasers, abbreviated as DHL. In double heterostructure lasers, CW operation at room temperature is possible. A thin layer of the active medium, for example, 0.1 to 0.2 micron in thickness of the gallium arsenide, is sandwiched between P and N materials made from aluminium 0.3, gallium 0.7, and arsenide. The relevant structure is shown in part A of figure 4. So this is part A of figure 4, and the caption of the figure 4 is layer structure of DHL, double heterojunction laser, with gallium arsenide as the active medium in part A and indium gallium arsenide phosphate as the active medium in part B. So this is part A. You can see the thickness of these materials. 1 micron for the P type of material, 1 micron for the N type of material, and the thickness of the middle layer, which is the gallium arsenide layer, is 0.1 micron. And the substrate here is substrate is N type gallium arsenide. Whereas in the other junction where we are using indium gallium arsenide phosphate as the active medium, you can see that we have the P type of material made up of indium gallium, indium phosphate, and of course the N type of material is also from indium N type is also from indium phosphate, and then the middle layer, that is the junction layer, is made from indium 1 minus X, gallium X, arsenide Y, and P as 1 minus Y, because the X and Y descriptions will be, the details about X and Y will be given in the description. And the substrate is again N-type indium phosphate. A thin layer of the active medium, 0.1 to 0.2 micron of gallium arsenide, is sandwiched between P and N material made from aluminium 0.3, gallium 0.7 arsenide. The relevant structure is shown in part number A, which I have just shown you. In a second option, a thin layer of indium gallium arsenide phosphate is sandwiched between P and N side materials made from indium phosphate. The relevant structure is shown in part number B. This is also what I have shown you. I have shown you part number A and also part number B. Typical values of current densities for these structures is of the order of 10 to the power 3 ampere per centimeter square, which is 2 orders of magnitude smaller than the corresponding current densities in a Homo junction layer. This makes the CW operation possible in DHL at room temperature. In DHL, the laser beam remains confined within the active layer because the refractive index N1 of the active layer is significantly larger than the refractive index N2 of the cladding layer. So you see that P side and N side will be referred to as the cladding layer, having refractive index that of equal to N2, whereas the active medium layer has a refractive index as that of N1, where N1 is much less than N, where N1 is much greater than N2. In DHL, the injected holes and electrons remain confined within the active layer because of the energy barriers at the interfaces between the active layer and the P side and the N side layers. So you see that energy barrier is established between the interface of the active medium layer and the P sides and the active medium layer and the N side materials. The band gap energy, which is Eg1 of the active layer, is significantly smaller than Eg2, that is the band gap energy of the cladding layers. And this Eg2 is for the p-type of material and for the n-type of material, whereas for the active material, the energy gap is Eg1. So the band gap energy Eg1 of the active layer is significantly smaller than Eg2 of the cladding layer. This gives rise to the formation of energy barriers at the two junction planes. So you see that energy barrier is created at the two junction layers. That is between the active medium and the p-type, and the active medium and the n-type material. The frequency of the laser beam, which is given by nu is equal to Eg1 over h, which has its wings in the cladding layers. And we know that for the cladding layer, Eg2 is much greater than Eg1. The absorption of the beam wings is significantly weaker in the cladding layers. The free carriers in the cladding layers, however, weakly absorb the laser beam at its wings. The above factors are responsible for CW operation of the DHL at room temperature. Because of the weakly absorption wings of the laser beam by the cladding material. This factor makes the laser operation of the laser operation in CW for the DHL material at room temperature. To form structure in DHL, the lattice period of the active layers must equal to within 0.1% of the cladding layers. If this condition is not fulfilled, dislocations of the two interfaces where the electron hole non-radiative recombination occur are created. Now consider the layer structure of DHL, in which the active layer is indium gallium arsenide phosphate, and the p-type and n-type materials are made from indium phosphate as shown in part number B. So let me show you part number B again. You see that the p-type and n-type materials are made from indium phosphate, and the active medium is made from indium gallium arsenide phosphate. The lattice matching of the active layer with those of the cladding layers is not described. Assume that in indium phosphate as the active layer, some fraction x of the gallium is added, giving indium 1 minus x gallium x and phosphate with a decreased lattice period compared to indium phosphate, as gallium has a radius smaller than the indium radius by about 19 picometer. Now consider Y of the arsenic is added, giving indium gallium arsenide phosphate. So you see that a Y fraction of arsenide is added, which will finally give you indium 1 minus x gallium x arsenide Y, and for 1 phosphate as with 1 minus Y concentration with increased lattice period compared to indium, which is 1 minus x gallium x and phosphate, as arsenide has a radius larger than P, radius by about 10 picometer. The values of x and y can be adjusted to keep the lattice period of indium gallium arsenide phosphate equal to indium phosphate by setting y is equal to 2.2x. So you see that if we set y is equal to 2.2x, then of course the lattice period of this indium gallium arsenide phosphate becomes equal to the indium phosphate. And you see that the ratio, which one is greater by what amount, has been described. For example, the arsenide has a radius larger than phosphate by a radius of the order of 10 picometer, whereas the whereas indium phosphate, whereas the gallium has whereas gallium is added, giving this one with a decreased lattice period compared to indium phosphate, as gallium has a radius smaller than indium radius by a factor by of the order of 19 picometer. So you see that here one has a smaller radius, the other has a greater radius. So you see that we set y is equal to 2.2x such that the lattice period becomes equal to that of the indium phosphate. Changing x or y while keeping y over x equal to the lattice matching condition, the band gap separation can be changed, and thus the wavelength can be varied from 1150 to 1670 nanometer for CW operation at room temperature. So you see that the condition is that y over x should be kept equal to the lattice matching condition. And then of course the band gap separation can be changed by changing x and y. We can change, but the ratio y over x should be kept constant. And then of course the wavelength can be varied from 1150 to 1670 nanometer for the CW operation of the laser at room temperature. Assume that a current density J is flowing through the active layer of the thickness equal to D. Rp, the rate of electron and hole injection per unit volume into the active layer. So Rp is what we call it as a rate of electron and hole injection per unit volume into the active layer is given by. So we have Rp is equal to eta times I times J divided by Ed, where E is the electron charge and eta I is the internal quantum efficiency, whereas the other variables have been defined. Under steady state condition, the carrier density N is related to Rp through the radiative recombination time tau Rs. So you see that this is the relationship between the carrier density N and Rp, which is the rate of electron and hole injection per unit volume into the active layer. So this is the relationship related through the variable tau R, where tau R is the recombination time. So using from equation number 4 and 5, using equation 4 and 5 and eliminating Rp, we get the equation number 6, which gives you the current density J is equal to E times D times N divided by eta I times tau R. So this is the relationship that will give you the relation of the current density in terms of the parameters of the electron charge, the layer, the thickness of the layer, junction layer, or the active medium layer, and is the concentration of the charge carriers. It is the quantum efficiency, tau R is the radiative recombination time. From which the threshold current density can be found as. So we can write down the subscript thresh with J. So J threshold is equal to Ed over eta I into tau R, and we have given a subscript as a threshold to the variable N. So we have, so you see, you can compare the last two relationship, which are the same, but is that we have put a threshold parameter with the current density and also with the variable N, which is the carrier density. So we have J thresh is equal to Ed over eta I into R related with the N thresh. The derivation of equation number 7 assume that all the carrier recombination in the active layer occurs radiatively. So you see that this is important, because if the recombination is non-radiative, that is not useful for the as far as the laser process is concerned. So we want to have a radiative emission, and for that is a combination, that is the recombination should be radiative, and for that the equation number 17 is described. At large D, the N threshold is approximately equal to N transparent is equal to constant. So if D is very large, then of course the threshold value for the threshold value for the charge density, for the carrier density, which is n threshold, is the same as that of the transparent density at which the semiconductor becomes transparent, and of course this is constant. From equation number 7, J threshold is directly proportional to D, but when D becomes significantly small, the confinement action of the active layer becomes ineffective and the beam extends into the P and N sides. The effective gain reduces and losses in the cladding layers increase. So you see that main objective is that we should keep the beam confined in the active region, and the beam should not penetrate into the p-type material and n-type material where it can significantly contribute amount of energy, and of course the system becomes inefficient and the effective gain reduces and the losses in the cladding layer increases. So I would like to here describe that the detail about the semiconductor materials and that of the quantum well have been described in slide number 67, slide number 68, 69, and slide number 72. I would suggest that if you want to read this presentation, you are required to go through first the slide number 67, 68, 69, and 72, so that you can understand the basics of the semiconductor materials, of the Homo junction and the Hetero junction and the quantum well lasers also, and the quantum well semiconductors also. Now, quantum well lasers. A DHL, that is double heterojunction laser with active layer dimension comparable to de Broglie wavelength, which has a lambda of the order of h over p, where p is the momentum of the electron, is regarded as QWDHL, that is the quantum well DHL, provided the active layer has a dimension of the order of lambda, and here lambda is the de Broglie wavelength. Then we call such a DHL as quantum well DHL. Quantum QW, quantum well lasers have increased differential gain with weaker dependence on temperature. So you see that this is the main advantage, that there is a weaker dependence upon the temperature, and we have an increased differential gain. These properties may be related to the density of states of the quantum well materials. Quantum well confinement takes place in the well direction. So confinement factor strongly affects in the well direction. Confinement factors strongly affects the properties of the quantum well lasers. Many structures are possible, and a simple one is shown in part number A of figure number 5. So this is figure number 5. This is part A of figure number 5. So let me read the caption first. Energy bands of quantum well heterostructure with step indexed confinement in part A. So you can see that this is a step indexed confinement. So you can see that this is a step over here. Similarly, you can see a step over here. So this is a step indexed confinement. The effective layer is made from gallium arsenide and graded index confinement in part B. So you can see that this structure is that of the graded index confinement, because the index is not changing rapidly, but the index is changing very slowly. So that is why it is called graded indexed confinement, as shown in part number B. The active layer is made of gallium arsenide, and the P and N sides are made from aluminium X, gallium 1 X, and arsenide. Optical mode intensity profile is also shown by dashed line in part number A. Optical mode intensity profile. So the optical mode intensity profile has been shown for part number A. So you can see that this is the intensity, and this intensity is gradually, you see, decreasing. It is the maximum in the center of this index in gradient index region. In the center of that one, the beam intensity is maximum, and away from that one, you will see I have also shown 1 over e square points where the intensity drops to 1 over e square on both sides of that one. Those points have also been shown. And you see that in this figure, the position on the horizontal axis is from -1 to +1 micron, and the index occurs, the center of the index occurs at the center of that position. And we have shown the EV, that is the energy in the valence band, and the energy of the electrons in the conduction band. So this is the location of the conduction band has been shown. And this is the energy of the valence band from where the bottom of the valence band starts, that has been shown over here. And this is the bottom, or this EC corresponds to the bottom of the conduction band, which has been shown as step in text. Similarly, the same parameters have also been shown for the part number B. So EV is actually the energy corresponding to the bottom of the valence band, and EC is the energy corresponding to the bottom of the conduction band. And you see that there is a well over here. So this is the well in the corresponding to the valence band. This is the well in the conduction band. Similarly, and these are of course gradient indexed wells. And in part number A, we have step indexed wells, both in the conduction band. The upper one is in the conduction band, and the lower one is in the valence band. At the center, a thin gallium arsenide quantum well of the order of 10 nanometer is located on both sides of quantum well. So you see that you can see this is the quantum well in the center. This is quantum well. This is quantum well. This is the quantum well in the conduction band. This is the quantum well in the valence band. And similarly for the gradient indexed type, this is the quantum well in the conduction band. This is the quantum well in the valence band. And these two bands has a width of the order of 10 nanometer, and the thickness of the material, for example, at the center, a thin gallium arsenide quantum well of the order of 10 nanometer is located. On both sides of the quantum well, there are two thick layers of the order of 0.1 micron inner barrier layers of wider band gap materials. And the material is aluminum 0.2, gallium 0.8, and arsenide, which has lower refractive index in comparison with the refractive index of the thin layers of the gallium arsenide quantum well. So you see that the thickness, you can see that the thickness of these barrier layers of wider band gap material is of the order of 0.1 micron, which is 10 times that of the, which is about how many times you can clearly find out from here. Next to these layers, there are two much thicker 1 micron cladding layers. So you see that here we are cladding layers, that we are talking about the P layer and the N layer. So next to these layers, so you see that I have shown the two layers in this figure. For example, in this figure, I have shown the layer of the central region, that is the layers of the quantum well, and the wider junction around that one. But of course, beyond that, these regions, that is on the right hand and the left hand side of these regions, there is a thicker material of the P type and N type colliding materials, and that is made of aluminum 0.6, gallium 0.4, and arsenide, forming P and N sides of the diode. The higher refractive index of the inner barrier layers in comparison with the colliding layers provides a means of beam confinement. The beam intensity profile for this waveguide configuration is shown by the dashed line. So you see that I have also shown the intensity profile for this waveguide configuration has been shown in dashed line. This intensity has been shown. of the beam, and you see that the beam intensity at a region falls over here and becomes nearly and becomes of course zero before it enters the p type or p region and the n region on both on either side of this one. So there is a p region, for example, and the n region on the right hand side of this region, and then of course the intensity of this beam will not enter into that one because it has decayed almost within that region. So the beam confinement has occurred. The beam intensity profile for this waveguide configuration is shown by the dashed line. More useful structure known as the graded index separated confinement heterostructure is shown in part number B of figure number 5, which I have explained. The refractive index of the inner barrier layer gradually changes from quantum well interface to the interface between the two cladded layers where it matches the index of the cladding layer. Beam confinement. Beam confinement by step indexed or graded index profile, whereas carriers are confined by the quantum well structure. Beam is confined by the step indexed or graded index profile, whereas carriers are confined by the quantum well structure. J threshold is reduced by a factor of 4 to 5 compared to J threshold as used in a double heterostructure laser due to reduction in the active layer thickness. The thickness of the quantum well layer is smaller than the width of the beam, and the beam confinement is achieved partially by a separate confinement structure. Due to quantum well structure, the differential gain increases by a factor of 2 compared to the corresponding bulk material. A multi-quantum well, which we call as MQW, structure consists of a number of alternating layers of narrow and wide band materials. The thickness of each QW is around 5 nanometer, while the thickness of the wide band gap barrier is around 4 nanometer. This is enough to prevent quantum well tunneling of electrons from one well to the next well. In quantum well lasers, lattice matching condition is relaxed up to 1 to 3% without creating misfit dislocations at the boundaries between the two materials. The lattice mismatching produces a strain in the structure, resulting in strained quantum well. Strained quantum well have also been explained in one of the previous slides, for example, maybe in slide number 68 to 72. So strained quantum well lasers can be used to extend the wavelength range covered by the unstrained quantum wells. The strained quantum wells, the effective mass of the hole in the junction direction becomes nearly equal to the effective mass of the electron. This lowers the value of the N transparency, that is the value of N transparent region and transparency, and enhances the differential gain sigma. Lower threshold current density is needed for laser operation from a strained quantum well at higher efficiencies. So this is an advantage of the strained quantum well, that the efficiency is much greater because of the narrowness of the because of the enhancement of the differential gain and also the narrowness of the active region. A few words on the application area are now presented. In DHL and quantum well lasers, the laser material is characterized by the combination of active layer and the substrate. In both cases, laser wavelength is mainly determined by the refractive index of the active layer. In quantum well lasers, the thickness of the active layer is also important in the wavelength determination. For better laser beam confinement, separated confinement in quantum well and multi-quantum well is preferred. Single strip semiconductor devices, which have also been discussed in slide number 67 to 69, single strip semiconductor devices are widely used in CD players and in laser printers, laser arrays, laser bars, and stacks of laser bars, which also have been discussed before slide number 67, are used to pump different types of solid state lasers. Active layers may be based on a range of materials with corresponding materials for P type, P side, and N side, and provide a wide range of wavelengths, some of which are appropriate for fiber-based communication. Most lasers operate at room temperature, with the exceptions of a few which require cryogenic temperature, that is lower temperature. In short, uses of semiconductor lasers are enormous. So you see that here is a good news for you that this is the last slide of the course on laser physics. So I have tried my best to present all the necessary theoretical features or theoretical aspects of the laser physics. You must, if you want to understand and if you want to get full benefit of this course, you should start this course from slide number 1 and should end this course at slide number 144. So under this condition, you will be able to understand the laser physics fully, and you will be able to carry out research in the field of laser physics also. So this is the last slide of the course on the laser physics. And of course, this is also the end of slide number 144. So good luck with this course.